Okay, so in this lecture, we're going to be continuing our discussion of voltaic cells. And we're actually going to sketch a voltaic cell based on the reaction that we talked about in the last lecture. So the reaction that we talked about in the last lecture, if you recall, was the reaction in which silver plus 1 ion from silver nitrate is reduced by copper metal to make silver 0, and copper 2 plus is also produced in the process. So we were talking about how that reaction produces a lot of energy. It's very spontaneous reaction. Can we harness that energy to do useful work and make a battery? So battery. So now we're going to sketch a voltaic cell, also known as a battery, in which we do just that. So what we have to do is separate the two reactions so that we're basically making two half reactions. And the oxidation reaction is going to occur at one electrode, which I'm going to call the anode. The reduction half reaction is going to occur at the other side, at the other electrode, which I'm going to call the cathode. What this means is the anode is where the location where oxidation occurs. Okay, so oxidation occurs at the anode. So that's something you should know, that oxidation occurs at the anode. Reduction occurs at the cathode. Sometimes I have heard a mnemonic device, red cat, reduction occurs at the cathode. That might help you remember which is which. Remember, Leo, the lion goes grr, also lose electrons, oxidation. So oxidation is occurring at the anode. Those terms are really important because, you have to know where the electron flow is going. Okay, so here, my dielectric medium here is the solutions that I've drawn in these two beakers. So we have aqueous solutions in these two beakers. And I'm also going to draw metal electrodes kind of sticking into those two beakers. So here I'm making these two metal electrodes. Now, oftentimes you just use like a precious metal like platinum for your metal electrode. However, here, because we're actually talking about solid metals, at the anode, I can actually have my electrode be made out of copper. So we're going to have this electrode be made out of solid copper. And the solution is going to be the copper 2 plus that is kind of occurring as that is coming out as the electrode is dissolving, because the copper 0 is getting oxidized to copper 2 plus over the course of the reaction that we just talked about. So oxidation occurs at the anode. That means that the copper 0 in the electrode here, I'm going to color it in a little coppery color so you can imagine that this is your copper electrode. As this copper gets oxidized, it releases the Cu2 plus in solution, and it also releases electrons. Now, the electrons are going to start flowing out. And what you usually have in a battery, hang on a second, is a voltmeter kind of measuring the electron flow. Oops, here. My drawing is being thwarted. So here I'm just gonna write a big V for voltmeter kind of. What we have is electrons flowing from the anode to the cathode. And as those electrons flow from the anode to the cathode, those electrons are going to reduce the silver plus 1 to, let's get a nice silvery color, to silver 0. So we cannot even have this electrode be made out of silver. And as the redox reaction progresses, that silver electrode is going to bulk up. So this is my silver electrode, and it's going to kind of bulk up as the silver from the solution plates out onto it. Okay? So the direction of electron flow is always going to be the same. Electrons are always going to flow from the anode where oxidation occurs to the cathode where the reduction occurs to the cathode. Now, we have a weird charge imbalance happening, right? You can imagine as the electrons are flowing this way, you get a lot of buildup of negative charge on this side and depletion of negative charge on this side. So in order to complete my voltaic cell, I need to add something special called a salt bridge. Now, a salt bridge is something that is not reactive, but that connects the anode and the cathode so we can maintain charge balance. Usually it's made out of some kind of non-reactive salt. Potassium nitrate is very common. So what will happen is the nitrate, being the negatively charged ion, will kind of flow into the anode to replace the negative charge that's lost as the redox progresses. And conversely, the potassium, which is a positively charged ion, will flow into the cathode to kind of balance out the negative charge that's accumulating at the cathode. So a salt bridge just has to be made out of some inert salt, and it has to allow the ions to pass through so that both sides can be maintained at neutral charge. Okay, so as this redox reaction progresses, the reaction, the half reaction, I should say, the half reaction that occurs at the anode is the oxidation of copper. So copper 0 is going to, oops, don't know what that one is. Copper 0 is going to copper 2 plus with a consequent loss of 2 electrons. At the cathode, the half reaction that happens is that silver plus 1 is gaining an electron to make silver 0, and that plates out onto the electrode. Oops. Okay, so that plates out onto the electrode. So you'll actually see the silver plating out as a solid on the metal electrode surface. So the copper electrode here is going to shrink, right? It's literally dissolving. The copper 0 is dissolving and it's becoming Cu2+. So this electrode is going to shrink. This one's going to bulk up. So the voltmeter here measures what's called the cell potential. Okay, so let's talk about the voltmeter for a second. And we'll talk about what the cell potential means. So the voltmeter measures what's called the electrochemical potential of the cell. Sometimes we just abbreviate that as cell potential. We abbreviate it as a delta, capital Greek letter, epsilon. Now, we also will call cell potential voltage. Sometimes I'll just say voltage a lot of times. Cell potential and voltage are exactly the same thing. And it's important to note that a voltaic cell or a battery is going to have a different voltage depending on the materials that are used to make it. So, for example, let me give you a couple of examples of different anodes and cathodes and the measured cell potential of each one of these. So, if we use zinc as our anode and copper, as our cathode, you get a measured cell potential of 0.950 volts. This is volts named after Alessandro Volta. So if your anode is magnesium and your cathode is copper, you get a cell potential of 1.660 volts. Ooh, so that's a better battery. If your anode is magnesium and your cathode is zinc, then you get a cell potential of 0.68 volts. So just looking at these measured cell potentials for these various voltaic cells, you can see that voltaic cells have different voltages depending on the materials that they're made up of. And it's also important to see that, look, you can actually tell by comparing these two top reactions here that magnesium prefers oxidation more than zinc does. So that's going to make a better battery. So magnesium prefers oxidation more than zinc. That's a bit anthropomorphic, but it makes sense. So if you had to choose between magnesium and zinc, like in the last example, zinc is going to be the cathode because magnesium prefers oxidation, so it will become the anode. And you'll get a cell potential that's lower, but still, it's going to be a voltaic cell. All right, so in your book, you have a whole table of standard reduction potentials. This is in the appendix of your book. It's also in the reference tables in OWL. And these are standard reduction potentials at 25 degrees Celsius in aqueous solution for many common half reactions. Okay, so this is not the exact same table as your book, but it has the same information. And what this has is the electrochemical potential for half reactions. Okay, so notice all of these reactions have electrons floating around in them. So what you can do is use these standard reduction potentials to calculate the potential of various electrochemical cells based on their whole reactions using all of these values. These values assume standard conditions. So everything in this table refers to standard conditions. And for this table, that's defined as 1 atmosphere of pressure, a molar concentration of 1 molar for both the anode and the cathode solutions. That's extremely important because at the end of the chapter, we're going to be talking about non-standard conditions. So you just have to kind of realize that the standard conditions are 1 molar. And the other thing is that all of these in the table are at 25 degrees Celsius. So you will notice when you look at this table that some of the half reactions have positive voltages and some of them have negative voltages. And the 0 point in the table is defined as the standard hydrogen reference electrode. Oops, I did that funky thing with my pencil again. So I just want to highlight the 0 point here. Every electrochemical cell potential is measured in reference to this reaction, the standard hydrogen reduction. So this is the standard hydrogen reference electrode. And you can see that that reaction involves the reduction of 2 protons with 2 electrons to make 1 mole of hydrogen gas. So this is arbitrarily assigned a cell potential of 0 volts. Okay, so all the units here are volts. And then everything else is measured in relation to that. Okay, so I'll just show you the whole table. And in the next lecture, what we'll do is we'll do a couple of examples where we use this table to calculate electrochemical cell potentials for different reactions.